To gaze upward at the night sky is to behold an illusion of profound and perfect stillness. It is a deception woven from the very fabric of our perception, a cosmic sleight of hand performed on a stage so vast that its motion becomes invisible to the fleeting witness of a human lifetime. The stars, fixed upon their velvet backdrop, appear as timeless sentinels, their positions as permanent as the mountains, their light a constant, reassuring glow against the encroaching dark. The familiar constellations, those ancient patterns etched into human consciousness by generations of storytellers and navigators, return season after season with a dependable fidelity, a celestial calendar written in points of fire. The moon glides with a serene and measured pace through its phases, a silent metronome marking the months, while the planets, those wanderers, trace their predictable, looping paths against this static stellar tapestry, their journeys charted and anticipated by priests and kings. For millennia, this was the universe known to humanity, not a dynamic engine of change, but a great cosmic painting, a magnificent and unchanging spectacle hung above the world, a silent, permanent canopy under which the brief, flickering drama of life unfolded. This perception was not a naive assumption, not a childlike fantasy, but a conclusion drawn from the most direct and persistent evidence available to our unaided senses. The ground beneath our feet felt solid, immovable, the very definition of stability. The horizon stood firm. When we jumped, we landed in the same spot. The sun, the moon, the stars, they were the ones that rose and set, that marched in procession. Everything else, it seemed, moved around us. This deeply intuitive, egocentric view of a still Earth at the center of a revolving celestial sphere was so perfectly aligned with lived experience that it formed the unshakable bedrock of our earliest cosmologies, the foundation upon which we built our understanding of existence. We crafted myths of celestial chariots and divine beings, developed mathematics of cycles and epicycles, and constructed intricate philosophical models to explain a universe that seemed to orbit us, both literally and philosophically. The comfort this geocentricity provided was immense, a psychological and spiritual anchor. It placed humanity at the heart of creation, surrounded by an orderly, predictable, and divinely orchestrated dance, a performance staged for our benefit and edification. In that still center, we found meaning, purpose, and a sense of cosmic belonging. This geocentric view was a global phenomenon, a logical conclusion independently reached by cultures separated by vast oceans and epochs, each interpreting the same silent testimony of the heavens through the lens of their own unique worldviews. Servants of the Son of Heaven meticulously charted the heavens, developing complex systems of celestial bureaucracy where stars were mandarins and planets were imperial messengers, their motions predicting the fate of the empire below, weaving a philosophy where cosmic order mirrored terrestrial order. The Maya, with their precise, obsessive calendrical systems carved into stone, tracked the cycles of Venus with an accuracy born of the belief that the gods spoke through these motions, that the morning and evening star was a harbinger of war, of rain, of kingly fortune, a clockwork of destiny written in the sky. In the Indus Valley, Vedic seers describe a cosmos with Mount Meru, axis of the world, at its center, a cosmic pillar around which the sun, moon, and stars revolved, a spiritual geography mapping the metaphysical onto the physical. The Babylonians, pragmatic and precise, left behind clay tablets not of myth, but of data, meticulous records of planetary positions and eclipses, seeking patterns for prediction, for omen, laying the empirical groundwork for later theory. Yet it was within the intellectual ferment of the Hellenistic world, with its emphasis on geometry, logic, and philosophical reasoning, that this intuitive, almost universal picture was forged into a precise, technical, and breathtakingly comprehensive model of the cosmos. This intellectual edifice, a fusion of observation and idealism, would stand for over 1,000 years, not as mere superstition or primitive guesswork, but as the pinnacle of scientific thought of its age, a testament to the profound human drive to find mathematical order in the sublime, to cage the magnificent chaos of the heavens within a latticework of perfect circles and uniform motion. It was a system designed not just to predict, but to explain, to satisfy a deep-seated need for cosmic harmony and hierarchical perfection. The principal architect of this enduring monumental model was Claudius Ptolemy, a scholar of the 2nd century CE, living and working in Alexandria, the great intellectual crossroads of the Roman Empire, where the scrolls of the world gathered in the great library. Ptolemy was less a radical innovator and more a supreme synthesizer, a brilliant compiler who stood upon the shoulders of giants, distilling centuries of accumulated wisdom into a single definitive framework. He inherited the millennia of astronomical observation from the Babylonians, their numerical precision. He absorbed the geometric traditions and philosophical underpinnings of the Greeks, from the intuitive nested spheres of Eudoxus to the sophisticated trigonometric calculations of Hipparchus, who first discovered the precession of the equinoxes. From the Egyptian traditions, he drew upon a long, unbroken history of practical sky watching tied to the flooding of the Nile. Ptolemy's genius lay in his ability to weave these disparate threads, the empirical, the geometric, the philosophical, into a single coherent and mathematically rigorous tapestry, a cosmic mechanism that could account for the observed motions with formidable accuracy. His monumental work, the Mathematique Syntaxis, known to later ages by its Arabic-derived title, Almagest, the greatest, became the definitive word on the universe, the astronomical Bible of the Western and Islamic worlds. It was a cosmic blueprint so effective, so complete in its explanatory power, that it would dictate humanity's place in the cosmos from the height of Rome through the Middle Ages and into the dawn of the Renaissance, an orthodoxy so entrenched it became indistinguishable from reality itself. To question it was not merely to dispute a scientific theory, it was to challenge a fundamental pillar of understanding, a worldview sanctioned by both reason and, in time, religious doctrine. In the Ptolemaic model, the universe was a place of exquisite, hierarchical perfection, a physical manifestation of Aristotelian philosophy and Platonic ideals. At its absolute center, motionless and immutable, sat the earth, a sphere of rock, water, and air, corruptible and changeable, the realm of generation and decay. This central position was not a suggestion, but a geometric and philosophical necessity derived from Aristotelian physics. Heavy objects fell toward the center of the universe, and since all things fell toward Earth, Earth must be that center. Around this fixed, central point revolved a series of concentric, transparent, crystalline spheres, perfect and unchanging, made of a celestial substance called the quintessence, or ether. Each celestial body was embedded in its own sphere, like a jewel set in a spinning shell, carried around by the motion of its pristine crystalline carrier. The order was precise, sacred, and geocentric. The moon's sphere was closest, marking the boundary between the imperfect sublunary world and the perfect heavens. Then followed the spheres of Mercury, Venus, the Sun, Mars, Jupiter, and Saturn. Encompassing it all was the primum mobile, the prime mover, the sphere of the fixed stars, which rotated once daily from east to west, dragging the entire celestial machinery with it and producing the diurnal cycle of day and night, the most fundamental rhythm of human life. Beyond this outermost sphere of stars lay the Empyrean, the realm of the divine and the unmoved, forever inaccessible to human senses or inquiry, the source of all motion and the final cause of the cosmic dance. This was a universe governed by the aesthetics of perfection, perfect circles and uniform motion, for the circle was considered the most flawless shape, having neither beginning nor end, a symbol of eternity and divinity, and the heavens, by their very nature, had to partake in this perfection. Any deviation from circular uniformity was an affront to the cosmic order, a problem to be solved, not an observation to be accepted. Yet, the sky presented a stubborn, persistent complication to this ideal of perfect circular motion centered on Earth: the planets. The very word planet derives from the Greek for wanderer, and these wanderers exhibited behavior that was deeply perplexing, undermining the simple model of uniform circular motion. Observers tracking, for instance, the red, baleful glow of Mars over months would witness it steadily progress eastward against the star field, then slow, halt, reverse course in a distinct westward retrograde loop, pause again, and finally resume its eastward journey. This retrograde motion was a glaring anomaly in a cosmos supposedly governed by uniform circular motion around Earth. It was a hiccup in the celestial harmony, a moment of apparent defiance that demanded explanation. Ptolemy's solution was a masterpiece of mathematical salvage, a testament to human ingenuity in preserving a cherished paradigm against contradictory evidence. He introduced the concept of epicycles, a geometric device that added layers of complexity to preserve the core principle. A planet, he proposed, did not travel on a simple circle, a deferent, around Earth. Instead, it moved on a smaller circle called an epicycle, the center of which itself traveled along the edge of the larger deferent circle. This elegant, if increasingly complex, arrangement allowed a planet to occasionally loop back on itself as seen from Earth, beautifully replicating the observed retrograde motion. It was a cosmic dance within a dance, a celestial waltz of stunning intricacy where the planet pirouetted on its own little circle while that circle itself swept around the Earth. The epicycle was a brilliant fix, a mathematical epicycle that saved the phenomena, allowing predictions to match observations without abandoning the geocentric core or the circular ideal. But even epicycles were not enough to fully reconcile the model with the increasingly precise observations of later astronomers. The planets still seemed to vary in speed in ways a simple epicycle on a centered deferent could not explain. Their motion was not uniform even on the deferent. So Ptolemy introduced a second ingenious, yet philosophically awkward device, the equant point. The equant was a point placed symmetrically opposite Earth from the center of the deferent circle. The rule of uniform motion was then stated not from Earth, nor from the center of the deferent, but from this equant point, the center of the planet's epicycle was to move around the deferent with uniform angular speed as seen from the equant. This meant the motion was uniform from a point that was not the center of the circle, a subtle but profound deviation from the ideal of perfect Earth-centered circular motion. It was a mathematical fix that worked admirably for prediction, but it whispered of a universe whose mechanics were becoming alarmingly contrived, ad hoc, a patchwork of geometric corrections. It preserved the letter of the law, uniform circular motion, by violating its spirit, by moving the point of perspective away from the center. Nevertheless, the model held. It predicted planetary positions well enough for practical purposes like calendrics, navigation, and the all-important practice of astrology. It was taught in universities from Oxford to Baghdad, embedded in religious doctrine that saw in its hierarchy a reflection of God's plan, and served as the fundamental framework for understanding humanity's relationship with the divine and the cosmos. For over a millennium, the Ptolemaic universe was not just a theory, it was reality itself, a grand geocentric clockwork, complex but ultimately knowable, with humanity securely at its still and silent heart. The illusion of cosmic stillness was not an illusion. It was the foundational truth written in mathematics and confirmed by daily experience. The first quiet crack in this magnificent, millennia-old edifice appeared not with a shout of revolution, but with the hesitant, almost secretive publication of a dense, technical book by a dying man. The year was 1543. The book was De Revolutionibus, Orbium Coelestium, on the revolutions of the celestial spheres. Its author was Nicholas Copernicus, a Polish canon, lawyer, physician, and most significantly, a mathematician consumed by a quiet obsession. His revolutionary idea was deceptively simple in its premise, yet it threatened to unravel the entire cosmic order, to dethrone humanity from its privileged position. Perhaps the Earth was not the center of the universe. Perhaps the Sun was. Copernicus had arrived at this heliocentric hypothesis not through a sudden flash of inspiration, but through decades of quiet, painstaking study in his tower in Frombork, troubled by the growing complexity and philosophical inconsistency of the Ptolemaic system, particularly the arbitrary nature of the equant, which he saw as a violation of the very principle it sought to uphold. In searching for a model that adhered more purely to the Platonic ideal of uniform circular motion, he re-examined long-forgotten ideas from antiquity, from Aristarchus of Samos, who had posited a moving Earth, and found within them a new, startling geometric elegance. He realized that many of the complexities of Ptolemy's system vanished if one changed the point of view, if one exchanged the positions of the Sun and Earth. In the Copernican model, the Sun sat, unmoving, at or near the center of the cosmos, the true hearth of the universe. The Earth was demoted from its privileged pedestal, becoming the third planet orbiting the Sun, situated between Venus and Mars. This single, monumental transposition resolved the mystery of retrograde motion with breathtaking, elegant simplicity. Retrograde motion, Copernicus realized, was not a real loop in a planet's path, but a perspective illusion, a cosmic parallax, much like when a faster car overtakes a slower one on a highway. To a passenger in the faster car, the slower car appears for a moment to move backward relative to the distant landscape. As Earth, on an inner, faster orbit, overtakes a slower-moving outer planet like Mars, Mars appears to drift backward against the backdrop of the fixed stars. No complex epicycles were needed for this core phenomenon. It was a natural, inevitable consequence of orbital geometry when viewed from a moving Earth. The planets were not wandering erratically. They were all, including Earth, traveling on concentric circular paths around the Sun, their apparent wanderings merely a reflection of our own motion. Copernicus didn't stop with this grand reordering. He proposed 3 distinct motions for the Earth, transforming it from a static lump into a dynamic celestial body. First, the daily rotation on its axis, which explained the apparent rising and setting of the sun, moon, and stars in a far simpler way than a whirling cosmos of colossal spheres. Second, the annual revolution around the sun, which accounted for the seasons and the changing positions of the planets throughout the year. Third, a slow conical wobble of Earth's axis, known as precession, which explained the gradual shift of the pole star over centuries, a phenomenon known since Hipparchus, but now integrated into Earth's own kinematics. These were profound, radical insights that reframed fundamental human experience as a product of motion, not of stillness. The day was our spin, the year was our orbit, the slow drift of the heavens was our wobble. He even used the tools of trigonometry to estimate the relative distances of the planets from the Sun, constructing the first true-scale model of a solar system, revealing a vast, empty space between Saturn and the sphere of fixed stars. The universe, in his view, was almost unthinkably large, a necessary consequence to explain why no annual parallax, a shift in the positions of nearby stars due to Earth's orbit, could be observed. The stars were simply too far away for the shift to be detectable with the instruments of his time. Yet, for all its conceptual brilliance and philosophical elegance, the Copernican model had a critical, practical weakness. It was not significantly more accurate than Ptolemy's in predicting planetary positions. This was because Copernicus, still bound by the ancient, almost theological devotion to perfect circles, retained complex systems of small epicycles and off-center circles to fine-tune the orbits, to account for the same irregularities that troubled Ptolemy. His universe was sun-centered, but it was not simple. It was a new arrangement of circles, not a wholesale rejection of them. Furthermore, the idea of a moving, spinning Earth flew in the face of both entrenched Aristotelian physics, which argued that a rotating Earth would fling objects into the air, that arrows shot vertically would land far to the west, and that the very air would be left behind in a perpetual hurricane, and literal interpretations of scripture that spoke of an Earth that cannot be moved. Copernicus was acutely aware of the theological and physical controversy his book would provoke. Legend holds he first saw a printed copy on his deathbed, perhaps a final act of caution or a poignant symbol of his lifelong hesitation. His work was a revolutionary seed, a quiet, mathematical argument, but it lay dormant for decades, a tantalizing, heretical hypothesis awaiting physical proof. That proof would come not from better mathematics alone, but from a new way of seeing, from an instrument that would extend human vision and place empirical evidence before philosophical preference. The Copernican revolution needed a witness, and that witness would be a stubborn Italian physicist with a talent for building instruments and a flair for confrontation. The instrument that would irrevocably shatter the crystalline spheres of Ptolemy was, at first, a mere curiosity, a toy. In the early 1600s, news reached the Venetian Republic of a Dutch device that used a combination of lenses to make distant objects appear closer. Galileo Galilei, a professor of mathematics in Padua, seized upon this novelty, understood its optical principles, and radically improved its design, grinding his own lenses to achieve a clarity and magnification far beyond the original spyglasses. What he did next was an act of profound intellectual courage and curiosity. He pointed his telescope not across the Venetian lagoon to scout ships, but upward into the depths of the cosmos. The heavens, when magnified, were not the smooth, perfect, immutable realm of Aristotle and Ptolemy. They were a new world, dynamic, textured, and flawed, breathtakingly familiar in its imperfection. Galileo's moon, when viewed through his lens, was not a perfect, luminous orb of quintessence. It was a world. Its surface was rugged, marked by vast, shadow-casting craters, towering mountains that cast long shadows, and deep, dark valleys, a landscape eerily similar to that of Earth, complete with what he mistakenly thought were seas. This alone was a revelation that challenged the fundamental philosophical divide between the corrupt, changeable terrestrial realm and the perfect, immutable celestial one. If the moon, a celestial body, was marked and scarred, then the heavens were not perfect. The first crack in the crystalline spheres was a crack in the lunar surface. Then, in January of 1610, he turned his telescope, now with improved power, toward the bright planet Jupiter. He saw not just a disk, but a small, miniature system of its own, 4 points of light, arrayed in a line near the planet, steadfast in their alignment. Night after night he tracked them. They changed position, dancing around Jupiter, but they never left its vicinity. He had discovered 4 moons orbiting another world, bodies that clearly were not circling the Earth. This was a revelation of monumental cosmological importance. It was a tangible, observable counterexample to the geocentric dogma. If moons could orbit Jupiter, then not everything in the cosmos revolved around Earth. Jupiter was its own center of motion, a miniature solar system that demonstrated in the stark clarity of the eyepiece the principle of celestial bodies orbiting a common center of gravity. The Earth's unique cosmic centrality was broken. It was a planet among planets, a center only to its own moon. The crystal spheres, if they existed, would have to intersect in impossibly complex ways to allow Jupiter's moons their dance. It was simpler, Galileo argued, to discard them altogether. The final, decisive observational blow to the geocentric model came from the planet Venus. Through his telescope, over months, Galileo observed that Venus exhibited phases just like our moon, cycling from crescent to gibbous to full and back. Crucially, these phases correlated perfectly with its apparent size in the sky. When Venus appeared as a small, full disk, it was distant on the far side of the Sun. When it was a large, thin crescent, it was close, positioned between Earth and the Sun. This precise correlation between phase and angular size could only be explained if Venus orbited the Sun, illuminating different portions of its sphere from our viewpoint. In the Ptolemaic system, where Venus's epicycle was placed between Earth and the Sun to explain its limited elongation, the planet would always appear as a crescent or a half-disk, never full, and its size would not vary so dramatically. Galileo's observations, published in his revolutionary pamphlet Sidereus Nuncius, Starry Messenger, and later works, provided the tangible visual evidence that tipped the scales from philosophical debate to empirical fact. The Copernican hypothesis was no longer just an elegant mathematical alternative. It was a description of physical reality confirmed by the direct testimony of light itself. The Earth was in motion, but the question of how it moved, the precise mathematical laws governing that motion, the exact shape and speed of the planetary paths remained unresolved. That monumental task fell to a different kind of genius, a man who saw divine harmony in numbers and geometry, a contemporary of Galileo working not with a telescope, but with the most precise naked-eye observational data ever collected, the legacy of a Danish nobleman with a golden nose. Johannes Kepler, a German mathematician, astronomer, and mystic, was a man consumed by a passionate, almost poetic search for cosmic harmony. He was deeply religious, a Lutheran who believed God had created the universe according to a beautiful, intelligible geometric and musical plan, a cosmographic mystery waiting to be decoded. He became an assistant to the last great pre-telescopic astronomer, Tycho Brahe, who had spent a lifetime on the island of Heaven compiling extraordinarily accurate positional data for the planets, particularly Mars, with an unprecedented precision reaching a few arc-minutes. When Brahe died under mysterious circumstances, Kepler, after some struggle, inherited this priceless trove of numbers, a treasure map to the cosmos. He set to work with fervor, trying to fit the orbit of Mars into the Copernican framework, assuming, as everyone did, that the orbit must be a combination of circles. He wrestled with the data for years, constructing model after model, but Mars refused to conform. The discrepancies were small, a mere 8 arc-minutes of deviation in the predicted position, but they were persistent, a nagging whisper that the model was fundamentally wrong. To Kepler, a man who trusted Tycho's data implicitly, those 8 arc-minutes were a crack through which a new universe would flood. Out of these 8 minutes, he would write, "We will construct a new theory of the whole universe." In a moment of tremendous intellectual courage, Kepler abandoned the 2,000-year-old dogma of circular motion. He let the data, the unflinching numbers, guide him. And the data spoke not of a circle, but of an ellipse. This was Kepler's first law of planetary motion. Planets move in elliptical orbits, with the Sun at one focus of the ellipse. An ellipse has 2 foci. The Sun sits at one, while the other is an empty point in space, a silent partner in the gravitational dance. This simple, profound shift from circle to ellipse banished the need for most of the complex epicycles and equants at a stroke. The orbit itself was an asymmetric loop, a stretched circle. The perfect circle was dethroned. Celestial perfection was found in a new, more subtle geometry. But Kepler went further. He realized that a planet does not travel at a constant speed along its elliptical path. It accelerates when it is closer to the Sun, at perihelion, and decelerates when it is farther away, at aphelion. His second law, the law of equal areas, quantified this beautifully. A line joining a planet to the Sun sweeps out equal areas in equal intervals of time. Imagine a planet moving in its elliptical orbit. The triangular slice between its position, the Sun, and its position a week later has a certain area. A week later, anywhere else in the orbit, the area swept out by that imaginary line will be exactly the same, even though the arc length along the ellipse is different. When close to the Sun, the planet moves faster to cover a longer arc and sweep the same area as it does when far away, moving slowly over a shorter arc. This was not just a description, it was a precise mathematical law of celestial acceleration and deceleration, a hint of a force emanating from the Sun that varied with distance. Finally, after more years of laborious calculation, driven by his search for harmony, Kepler discovered a relationship that wove the entire solar system into a unified mathematical whole. His third law, the law of harmonies, states that the square of a planet's orbital period, the time it takes to orbit the Sun, is proportional to the cube of the semi-major axis of its orbit, essentially its average distance from the Sun. In simpler terms, it provides a precise mathematical rule linking a planet's distance to its year. The farther a planet is from the Sun, the longer its year, and the relationship follows a specific, elegant power law. You could now calculate a planet's distance from the Sun simply by knowing its orbital period. The solar system was revealed not as a collection of independent cycles, but as a single, integrated dynamical system governed by a universal mathematical law. The music of the spheres was not a metaphor. It was a harmonic relationship expressed in squares and cubes. The work of Copernicus, Galileo, and Kepler collectively dismantled the still, Earth-centered universe. The Earth was now a traveler, a spinning planet orbiting a star, one member of a family governed by elliptical paths and precise laws. The Sun had taken center stage as the dynamical heart, the gravitational anchor of this new cosmic order. But in this new heliocentric model, a new stillness was implicitly assumed, a new fixed point. The Sun became the new anchor, the motionless heart of the cosmos, the unmoved mover of the solar system. For the next century, this was the accepted picture. Our solar system was an island of motion in a static void, with the fixed stars as a distant, unchanging backdrop, other suns perhaps, but unmoving in their infinite depth. Yet, the very success of this model soon raised deeper, more unsettling questions. If Earth was moving, and the planets moved, could the Sun itself also be in motion? Was our star truly fixed at the center of creation, or was it too a wanderer? And if so, against what backdrop, what absolute frame of reference could such a motion be measured? The search for answers to these questions would push astronomy beyond the parochial confines of the solar system, into the vast ocean of stars that was the Milky Way, and force humanity to confront the disorienting fact that there was no fixed point, no ultimate stillness to be found, that motion was layered within motion, a cosmic fractal of journeys. The man who first provided compelling, systematic evidence that the Sun was not a fixed point in space, that it, too, was a traveler, was an unlikely astronomer, a testament to the age of enlightened amateurs. William Herschel was born in Hanover, Germany, but made his career in England, initially as a musician and composer. His true passion, however, was the construction of telescopes, an art he elevated to a science. He became a master optician, grinding and polishing the finest speculum metal mirrors of his age, crafting instruments of unprecedented light-gathering power and resolution, tools that could see deeper into the stellar abyss than any before. With his devoted sister Caroline as his assistant, recorder, and later a celebrated discoverer of comets in her own right, he embarked on a monumental, almost unimaginably ambitious project, a systematic sweep of the entire heavens. Herschel's method was simple in concept, but exhausting in execution. He would point his magnificent telescope at a patch of sky and methodically count every star visible within its field of view, noting their brightness and distribution. Night after night, for years, he and Caroline mapped the stellar density, creating a statistical, three-dimensional picture of the starry realm, a census of the solar neighborhood. What he discovered from this vast accumulation of data was a pattern, a structure emerging from the apparent randomness. The stars were not scattered uniformly like dust across the celestial sphere. They were concentrated in a great, misty, irregular band arching across the heavens. The Milky Way, which transformed from a poetic smear of light into an architectural feature. In directions perpendicular to this band, toward the galactic poles, star counts fell off dramatically. From this statistical map, Herschel constructed a revolutionary model of the star system. He envisioned a vast, grindstone-shaped disk, a flattened collection of stars, an isolated island universe with the Sun positioned near its center. He had, in essence, deduced the shape of our galaxy from a position deep within it, like a single tree in a vast forest, deducing the shape of the woods from the density of trunks in different directions. While his scale was vastly underestimated, he could not account for the interstellar dust that dims and reddens distant starlight, making the galaxy seem smaller and the Sun more central. The conceptual leap was monumental. The universe was no longer just a solar system surrounded by a shell of stars. It was a structured, disc-shaped system of stars, a galaxy, a word derived from the Greek for milky. The Sun was not at the center of an infinite star field. It was a participant, a citizen in a grand, rotating assembly of suns. The question of solar motion then became inevitable. Even pressing, if we are part of a structured system, are we moving within it? Is the Sun stationary within this grindstone, or does it too orbit some more distant center? The definitive answer to the question of the Sun's motion came not from star counts, but from the meticulous, patient work of global astrometry in the 18th and 19th centuries, the precise measurement of stellar positions. The key was measuring proper motion, the tiny, almost imperceptible, gradual shifts in a star's position on the celestial sphere over decades or centuries. Its actual motion through space perpendicular to our line of sight. These motions are minuscule, measured in arc-seconds per year, where an arc-second is 1/3600th of a degree. To detect them required not just powerful telescopes, but precise, repeatable star catalogues compiled from observatories across the globe, a cooperative scientific enterprise spanning generations. Astronomers like James Bradley, who discovered the aberration of starlight, and later Friedrich Wilhelm Bessel, who first successfully measured the parallax of a star 61 Cygni, proving its distance, were pioneers in this exacting field. But it was the Dutch astronomer Jacobus Kapteyn who, in the early 20th century, synthesized vast amounts of proper motion data from many stars to analyze their systematic drift. He discovered that the stars were not moving randomly like a swarm of bees. Their proper motions showed a distinct pattern, a streaming which could most elegantly and simply be explained if the Sun itself was moving relative to the local stellar neighborhood. The apparent motions of the stars were partly a reflection of our own motion through them, a stellar wind in our face as we journeyed. He calculated this solar motion with precision, finding the Sun was heading toward a point in the constellation Hercules near the star Vega at a velocity of about 20 kilometers per second, a brisk cosmic pace. This direction is called the solar apex. The final vestige of cosmic stillness at our doorstep was gone. Not only was Earth moving and the planets moving around the Sun, but our star itself was a traveler, a ship cruising through the ocean of the galaxy, its motion betrayed by the subtle drift of the other stellar vessels around it. Captain, building on Herschel's work, but with better data, also used star counts and statistical estimates of brightness to construct a new, improved model of the galaxy, known as the Captain universe. It was again a lens-shaped disk, somewhat larger than Herschel's, but still with the Sun placed disconcertingly near its center. The reason for this persistent erroneous centrality remained a profound mystery, a fog that obscured our true place within the Milky Way. The breakthrough that would lift this fog, that would reveal the galaxy's true scale and our peripheral place within it, would come not from looking at the faint, distant stars in our own galaxy, but from studying those mysterious, fuzzy nebulae that dotted the sky, particularly the Great Spiral in Andromeda. Were they nearby, small clouds of glowing gas within the Milky Way, perhaps solar systems in formation, or were they something else entirely? Other island universes, galaxies in their own right, far beyond the borders of our own. This question, the great debate of the early 20th century, set the stage for the next great, breathtaking expansion of our cosmic horizon, a discovery that would redefine the universe once more, turning it from a single galaxy into a cosmos of galaxies, an archipelago in an endless sea. In the 1920s, using the powerful new 100-inch Hooker telescope at Mount Wilson Observatory in California, then the largest in the world, Edwin Hubble focused his attention on the great Andromeda Nebula, that faint smudge of light. Within its swirling spiral arms, he painstakingly identified individual stars, resolving its fuzzy light into distinct points. Among these, he found a special class of stars known as Cepheid variables, cosmic lighthouses whose behavior had been decoded by the brilliant Henrietta Swan-Leavitt at Harvard College Observatory. Leavitt had discovered a direct, precise relationship between the pulsation period of a Cepheid variable and its intrinsic brightness. The longer the period, the more luminous the star. By measuring the period of a Cepheid in Andromeda, how many days it took to brighten and dim, Hubble could determine its true, absolute luminosity. Comparing this known luminosity to its apparent, observed dimness in the telescope gave its distance via the inverse square law of light. The result, published in 1925, was staggering, paradigm-shattering. Andromeda was nearly 1 million light-years away, a distance so vast it was far, far beyond the conceivable boundaries of even Kapteyn's most generous model of the Milky Way. Andromeda was not a nebula within our galaxy, it was an island universe, a galaxy in its own right, a colossal spiral system of hundreds of billions of stars, comparable in size and structure to our own Milky Way. In an instant, the cosmos expanded by a factor of billions. The Milky Way was demoted from being the universe to being just one galaxy among countless others, a single spark in an immense, dark cosmic archipelago, a lonely city in a continent of cities. The universe had become a universe of galaxies. This new extragalactic perspective was utterly transformative. For the first time, we could see galaxies from the outside as complete structures. By studying the shapes, structures, rotations, and contents of other spiral galaxies, astronomers could infer, by analogy, the structure of our own Milky Way, which we are trapped inside and cannot see in its entirety. It was like finally understanding the shape and layout of the forest you live in by climbing a tall tree and viewing other similar forests from a distance. The work of astronomers like Jan Oort and Bertil Lindblad in the mid-20th century, using the motions of stars and interstellar gas clouds measured by radio telescopes, began to map our galaxy's spiral arms, its rotation curve, and its mass distribution. They found, conclusively, that the Sun was not near the center, but was in the galactic suburbs, about halfway out in the galactic disk, some 26,000 light-years from the core, orbiting the galactic center at a velocity of roughly 220 kilometers per second. One galactic year, the time for the Sun to complete one orbit around the Milky Way, is approximately 225 to 250 million years, a timescale that dwarfs all of human history. The last time our solar system was in this position in the galaxy, the continents were joined in Pangaea, and dinosaurs were just beginning their long reign on Earth. We are perpetually in motion, riding a galactic carousel that completes a single turn over geologic epochs, our motion so vast and slow it is imperceptible across 100 human generations. But what lay at the center of this great whirlpool of stars? This gravitational well that commanded the orbits of hundreds of billions of suns. For decades, the galactic center was a mysterious, powerful radio source known as Sagittarius A*, obscured by thick, swirling lanes of interstellar dust that blocked visible light. With the advent of infrared astronomy, which can pierce the dust, and especially the technique of very long baseline interferometry, VLBI, linking radio telescopes across continents, even across the Earth, to create a single Earth-sized virtual telescope with phenomenal resolution, astronomers could finally peer through the veil. What they found was a region of extreme violence and gravity. Stars were observed whipping around at thousands of kilometers per second, tracing tight, elliptical orbits around an invisible, incredibly compact, and monstrously massive object. The mathematics of orbital dynamics were unequivocal. An object with a mass over 4 million times that of our Sun was crammed into a volume smaller than our solar system. A volume so small that no conceivable cluster of normal stars or neutron stars could explain it. The only physical entity consistent with such an extreme concentration of mass is a supermassive black hole, a gravitational singularity cloaked in an event horizon, a place where space-time curvature becomes infinite. This cosmic monster, a dark engine of unimaginable power, is the silent anchor of the Milky Way, the pivot around which our entire galaxy and our Sun within it endlessly turns. Our grand, stately orbital motion is not just a journey through space. It is a dance dictated by the dark, relentless gravity of an abyss, a testimony to the power of nothingness. Our motion is orbital around a point of infinite density, a monument to Einstein's theory of general relativity made manifest on a galactic scale. Yet, the story of our motion, the layering of our journey, does not end at the galactic scale. The Milky Way itself is not adrift in stillness, a solitary island in a static void. In the same decade, he confirmed the existence of other galaxies. Edwin Hubble made another, even more profound and unsettling discovery, one that rewrote the story of the cosmos itself. By measuring the spectra of galaxies, breaking their light into rainbows, he and others like Vesto Slipher found that the characteristic lines in those spectra were shifted toward the red end, a redshift. This redshift was interpreted via the Doppler effect as a sign that the galaxies were receding from us. The shocking pattern that emerged was that nearly all galaxies showed this redshift. And crucially, the farther away a galaxy was, the greater its redshift, and thus the faster it appeared to be receding. This relationship, now known as Hubble's law, was not describing the motion of galaxies through a static space, like fragments from an explosion. It was evidence for the expansion of space itself, the very fabric of the cosmos stretching, carrying galaxies along like raisins embedded in a rising loaf of bread. The universe was not static, it was dynamic on the grandest possible scale. It had a history, a beginning in an event now called the Big Bang, and it was evolving, cooling, thinning out as it expanded. The Milky Way, therefore, is not just rotating, it is also being carried outward by this cosmic expansion, a participant in the great outflow from the primordial beginning. But within this general, smooth expansion, there are local currents and flows, gravitational eddies that superimpose specific, peculiar motions, deviations from the Hubble flow, as galaxies tug on each other across the voids. One such motion is both intimate to our local cosmic neighborhood and cataclysmic in its long-term implications. Our nearest large galactic neighbor, the Andromeda Galaxy, does not exhibit a redshift. It exhibits a blue shift. It is moving toward us against the grain of the general expansion. Precise measurements from the Hubble Space Telescope and more recently from the European Space Agency's Gaia satellite, which maps stellar positions with micro-arc-second precision, have confirmed the geometry and timing. Andromeda and the Milky Way are on a direct collision course, drawn together by their mutual gravitational attraction, which overwhelms the cosmic expansion on these relatively small scales. They are approaching each other at about 110 kilometers per second. In approximately 4 to 5 billion years, the two great spiral galaxies will begin a slow, majestic, gravitational merger, a ballet lasting billions of years that will twist and distort their spiral arms, fling stars into tidal streams, and eventually form a single, giant, featureless, elliptical galaxy, often nicknamed Milkdromeda or Milkomeda. This is not a catastrophic, fiery smash of stars. The spaces between stars within galaxies are so vast that direct stellar collisions are exceedingly rare, but a profound, stately restructuring of two cosmic ecosystems through the irresistible, sculpting force of gravity. Our solar system will likely be flung into a new, wider orbit within the merging wreckage, but it will almost certainly survive, bearing witness from within to a transformation of the night sky beyond all recognition, as the Andromeda Galaxy grows from a faint smudge to a dominating, splattered disk of light that eventually merges with our own Milky Way into a new, shapeless glow. But even this colossal, billion-year dance is merely a local phenomenon within a larger grouping. The Milky Way, Andromeda, the Triangulum Galaxy, and about 80 other smaller dwarf galaxies are gravitationally bound together in a small cluster known as the local group, about 10 million light-years across. This entire group, a few dozen galaxies held in a mutual gravitational embrace, is itself not at rest within the expanding cosmos. For decades, astronomers have mapped the peculiar velocities of galaxies, their individual motions relative to the smooth Hubble expansion. They discovered a vast coherent flow, a river of galaxies on a cosmic scale. Our entire local group, along with thousands of other galaxies in our vicinity, is being pulled, like water down a drain, toward a region of space in the general direction of the constellations Centaurus and Norma at a velocity of over 600 kilometers per second. This mysterious, hidden gravitational attractor, obscured behind the obscuring dust and stars of our own Milky Way's plane, was dubbed the Great Attractor. Later observations in X-ray and infrared, able to peer through the galactic zone of avoidance, revealed it to be not a single monstrous object, but a massive concentration of mass, a giant galaxy cluster, the Norma cluster, containing thousands of galaxies and part of an even larger filamentary structure called the Laniakea supercluster. Laniakea, a Hawaiian word meaning immeasurable heaven, is a cosmic watershed, a filamentary web of galaxies hundreds of millions of light-years across, containing perhaps 100,000 galaxies, all bound by gravity into a single flowing entity. We are part of this supercluster, and we are flowing along its gravitational watershed toward its dense center of mass, like a leaf caught in the current of a continental river system, drawn toward a distant, unseen sea. And the motion continues, upward in scale, ad infinitum. Superclusters, like Laniakea, are not isolated. They are the nodes and filaments of the cosmic web, the largest known structure in the universe, a foam-like network of galaxy filaments surrounding vast, empty voids hundreds of millions of light-years across. These structures, imprinted by quantum fluctuations in the first fraction of a second after the Big Bang and amplified by gravity over eons, are also in motion, tugged by even larger scale density fluctuations in the primordial universe. There are flows on scales of billions of light-years. The entire observable cosmos, some 93 billion light-years in diameter, is a dynamic, seething, flowing entity on scales that beggar the imagination. A symphony of motion with movements ranging from the spin of a planet to the drift of supercluster complexes. There is no center to this expansion, no fixed point, no privileged still frame of reference. Every atom, every planet, every star, every galaxy is in a state of perpetual layered, nested motion, spin on an axis, orbit around a star, rotation within a galaxy, galactic drift within a cluster, cluster flow within a supercluster, supercluster drift within the cosmic web, all superimposed on the relentless, accelerating expansion of space itself. We are travelers upon travelers, within travelers, carried by travelers. This brings us to the most profound and unsettling layer of cosmic motion, one that speaks not to where we have been or where we are, but to where everything is ultimately going, the final destination of all this grand, layered journey. In the late 1990s, two independent teams of astronomers, using distant Type Issa supernovae as standard candles, their known intrinsic brightness allowing precise measurement of cosmic distances, made a discovery that overturned the fundamental prediction of decades of cosmology. They found that the expansion of the universe is not slowing down due to the mutual gravitational attraction of all matter, as everyone had expected. It is accelerating. Some mysterious repulsive force operating on the largest scales is pushing space apart at an ever-increasing rate, as if the loaf of bread is not just rising, but the yeast within it is getting stronger. This force was named dark energy. It constitutes about 68% of the total energy density of the universe, and dominant, enigmatic presence that controls the cosmic fate. Its nature is perhaps the greatest mystery in modern physics. It may be a property of the vacuum of space itself, a cosmological constant as Einstein once envisioned and then discarded as his greatest blunder, a constant energy density inherent to empty space that causes repulsion. Or it may be a dynamic field that changes over time, dubbed quintessence. We do not know. The implications of this accelerated expansion are staggering, and they paint a haunting picture of the future of cosmic motion. If dark energy behaves as a true cosmological constant, its repulsive influence will grow as the universe expands and becomes more empty. Billions of years from now, the expansion will become so rapid that it will overcome all gravitational bonds, dissolving the cosmic structures that took so long to form. First, galaxy clusters will be torn apart, as the space between them expands faster than gravity can pull them together. Then, individual galaxies will be stripped apart, their stars flung into the expanding void. Later still, solar systems will be unbound, planets ripped from their stars. In an extreme, far-future scenario called the Big Rip, even atoms and atomic nuclei could be torn asunder by the relentless, exponential stretching of space itself, a final, catastrophic dissolution of all structure. The universe would end not in fire or ice, but in a ghostly, silent isolation of every elementary particle from every other, a death of relation itself, where motion becomes meaningless because there is nothing left to move relative to. An alternative, colder and perhaps more likely fate given current data, is the Big Freeze or heat death. In this scenario, the acceleration continues but does not become infinitely strong. The universe expands forever, but structures that are already gravitationally bound, like the Milky Way or Milk Dromedar, remain intact even as they become isolated islands in an ever-darkening sea. Stars will eventually burn through their fuel, dying as white dwarfs, neutron stars, or black holes. Over trillions of years, galaxies will darken. Black holes themselves will slowly evaporate via Hawking radiation, a quantum process that takes unimaginable lengths of time for supermassive black holes. Protons, the building blocks of atoms, may decay over even longer timescales, over timescales so vast they are meaningless to human intuition. Googles of years, a 1 with 100 zeros. The universe approaches a state of uniform, absolute zero temperature, maximum entropy. All differential motion ceases, all structure dissolves into a thin, ever-diluting haze of particles and radiation, a static, eternal equilibrium where no work can be done, no story can be told, no change can occur. It is an end of activity, of history, of journey. Motion gives way to a final, ultimate stillness, not at the beginning, but at the end of time. Yet another possibility, now considered less likely given the acceleration data, but still a subject of speculation, is the Big Crunch. If dark energy were to weaken, reverse, or if the density of matter were high enough, gravity could one day halt the expansion and pull everything back together in a cataclysmic, time-reversed contraction, culminating in a singularity mirroring the Big Bang, a big bounce, perhaps giving rise to a new cycle of cosmic birth and death, an eternal return, a phoenix universe where motion is cyclic, a great exhale following a great inhale. We do not know which of these fates, or another we have not yet imagined, awaits our cosmos. The ultimate destination of all this motion, the spinning, orbiting, flying, flowing, expanding journey of every particle in existence, remains the universe's final, unanswered question, a mystery written in the elusive nature of dark energy. We have only recently, in the grand span of human thought, awakened to the reality of this perpetual voyage. In a mere 5 centuries, we have peeled back the illusion of a still Earth under a fixed firmament to find a universe in a state of constant, dynamic, layered flux, from the quantum jitter of particles to the galactic whirl to the cosmic expansion. We are passengers on a planet that spins at over 1,000 miles per hour at the equator, a planet that orbits a star at 67,000 miles per hour, a star that moves through its galaxy at nearly 500,000 miles per hour, within a galaxy that rotates and falls and is carried by the expansion of space. The old, comforting, egocentric picture of cosmic stillness is gone, replaced by a story of magnificent, terrifying, and beautiful motion, a story in which we are both insignificant participants, tiny motes on a speck in an incomprehensible vastness, and privileged, conscious narrators, the universe's way of understanding itself, gazing out from our moving platform into the depths of a restless, ever-changing, dynamic cosmos. And as we look up at the seemingly static stars tonight, we can now understand with a shiver of awe that their apparent stillness is the grandest illusion of all, a trick of scale and time, masking a reality of unimaginable velocity and endless journey across billions of years. The universe is not a painting, static and framed. It is a river flowing from a distant hot source toward an unknown dark sea, and we, for our brief moment, are carried in its current, able to look, to measure, and to wonder. Good night.